Did you use the 37 centimeters for the, so it's still 4 foot?
Yeah. So the force of the plates I used were 37.
All right, are there any questions on the homework that is due today?
Could we do 4.4?
Okay. So. So this one is, and by the way, correct it with a different color pen if you wouldn't mind, okay? All right, the waiter. So we have an arm, we have a bicep, the tension force going upwards, here's the pin. The mass of the bicep, center of mass is
2.2.
yeah, the center of mass is here, and located 13 centimeters from the elbow joint. M1, I'm going to call it M1 is 2.2 kilograms. And how far away was the bicep?
3.5 centimeters.
And then there's double plates that are holding with 1.1 kilograms. And this is at a distance of 37 centimeters from the elbow joint. All right. And then this thing is accelerating upwards with acceleration equal to 0.9 meters per second. And then this thing is accelerating upwards with acceleration 2 equal to 2.5 meters per second squared. Okay. So that's what I get from the problem when I start to draw a picture of everything. Did everyone have something like this? I know it's pretty complicated. And so the idea would be, what's the force on the biceps? All right. So let's go ahead. Well, actually, let's see. What is the force being applied to the waiter's bicep? When we were dealing with statics. That's a good question. That's a good, because we didn't cover torques in the case where something's having some acceleration.
Acceleration, exactly.
Well, could you just use acceleration to solve for the force that's in the torque, or not? Like,
Well, we can give it a try and see what happens.
that times acceleration.
I
Is that
did
what
So
the,
we
I did the
can
mass
see
times
the force
acceleration,
that-
got the force, and then put that into the torque.
You can see the force that's applied here. You can see the force that's applied here. You know, that has to be applied to the arm to get to accelerate like this. And I guess that would tell us our total, we can figure out an upward force. The reason why this is probably not a good problem, actually, is that when we have a acceleration like this, we have to start talking about torque is equal to, I think, what's called moment of inertia times angular acceleration, which we never talked about.
So we should get rid of
For
it.
some reason, that didn't occur to me that may not be a good problem.
You should just make it extra credit.
No, I won't grade that problem.
Thank
What's that?
you.
You should just make it extra credit.
No.
All right, I'll do that.
Can we go over,
No.
You get it?
can we go over 4.5?
Did you get it?
We were just doing 4.8. Diagram
11.22.
I did it way wrong.
This is very interesting to me. They're all very. We didn't really cover any of that stuff. Because I thought it was statics, so.
Can we go over 4.5?
What's the answer?
Is that,
What's the answer?
you wanna go through this answer?
Yeah.
I just want to see if I got it right.
Yeah.
4.5.
Just say the answer.
All right, well, we can go through this real quick, if you want. We'll balance the torques due to all of this, okay? This may not make any sense at all to you guys, though. You wanna try it? I mean,
No.
No, I want to go over the ones that we already should have known how to do.
yeah. How do you do that? Yeah, because the forces, the problem with studying the forces equal to each other, the torques equal, is that this no longer applies. Some of the torques equal to 0, it's not the case.
Separate the force times r bar.
Actually, it would be some of the torques meters, what's called I times angular acceleration. And we can figure out what I is and what angular acceleration is. But that's completely outside the scope of what we've done.
So we shouldn't have been able to know.
Yes, I'm sorry I didn't
4.5
catch that earlier, okay? And if you struggled with that, I'm sorry. But it's probably not bad to at least get your head around the problem. So, so 4.5, a diagram of a hypothetical 40 centimeter long arm is shown. And then they show the biceps and everything. And it says, for the purposes of answering the question, assume that the arm itself is weightless, the muscle attached to the arm can contract at a rate of 7 centimeters per second with a force of 15,000 newtons.
I guess
Yeah.
that one's angular velocity too, I think.
What problem?
Yes, this one should be okay if we want to figure out what the angular acceleration is.
Or angular.
Cool.
And then what's the math? I think we can, this one too, part B has some troubles.
This will probably.
Okay, well, we can do, yes, I think we can do 4.5, assuming the maximum weight held isn't being accelerated, okay? So let's go ahead and do that one. All right, so 4.4, yeah, not that good. So that one will be any extra credit if somebody actually gets it. I'll produce a key that gets it, but if somebody, I'll be impressed if anyone gets it. Okay? Sorry about that. I know somebody came in for help and I thought, and I didn't look enough at it. All right, 4.5, a diagram of a hypothetical arm. So you have this muscle here. And this muscle can shrink, and it can contract at a rate of 7.0 centimeters per second. So this can shrink at 7.0 centimeters per second. So that means this thing can go up, at this point here, can move at 7.0 centimeters per second upwards. That make sense? This suspension point. All right, and it says, what's the maximum angular velocity of the arm if the muscle is attached 1 centimeter from the elbow? So that's 1 centimeter here. So if this is moving 1 centimeters per second and I'm attached here, you remember what the formula for angular velocity is?
V over R.
Omega is V over R, where R is the distance from the center of whatever is accelerating. So this point, so this would be the R. And then the whole arm would be moving with the same angular velocity. And so that would mean omega is 7.0 centimeters per second over 1 centimeter. And that would be 7 per second, which is 7 radians per second. Okay? So that's the angular velocity, part A. Part B, what's the maximum weight that can be held in the hand if the muscle is attached 1 centimeter from the elbow? So we're going to put a weight here. This force here, they said at maximum would be 15,000 newtons. We'll take this as our rotation axis. Yeah.
On your first one, don't you need to change 1 centimeter to 0.01 meters?
Well, luckily the centimeters cancel out
Oh,
with
sorry, I
this
thought that was a
ratio.
parenthesis for a second.
Yeah. Yeah, you're right. If I had to, if this were meters per second, I would have to change this to meters. Okay. So what's the maximum weight that can be held in the hand if it's attached 1 centimeter? Okay. So this arm is 40 centimeters long. All right, so we'll balance the torques here. So what's the torque due to this arm, to this thing?
15,000 times 0.01.
Yeah.
0.01.
0.0.
Yeah, that's right. So the torque due to the muscle is, and it would be positive, it'd be 15,000 newtons times 0.01 meters, which is 150 Newton meters, right? And it's positive. And then the torque due to the weight, let's do torque due to mass. This would be, it's negative because it makes it want to rotate clockwise, right? It would be negative. What's the force here? mg
Yeah. Times.
times 0.4 meters. And then the sum of the torques has to be 0.
Mhm.
So I would get 150 Newton meters minus mg times 0.4 meters is equal to 0. And I want to figure out what this m is, right? So I would take, I'd bring this over to here, and I'd get 150 Newton meters is equal to mg times 0.4 meters. This would be, this is what I'm looking for, this is 9.8 meters per second squared. And so I'd get that m is 150 Newton meters divided by 9.8 meters per second squared times 0.4 meters is m, and that'd be the answer. What would you get? What's that?
Yeah, that's what I got.
Kilograms, and so that'd be on the order of, yeah, 80 pounds. It's actually pretty heavy. All right, and it says, what if, the next part is, what if instead of this being 1 centimeters, it was 3 centimeters? In this case, my angular acceleration would be significantly less because I'd be dividing by 3 here instead of 1. And so this would be 7/3 radians per second. And so that would be, what, 2 1/3? All right, and then torque, I'd do the same thing, but instead of having 1 here, I'd have 3. So bigger torque due to the muscle, and I'll be able to get, should be able to get factor of 3, bigger mass I'm holding roughly, right?
Big enough?
Yes. Right, because I'll put a 0.3 here, which would be 450, right? And then, so I put a 450 here. And everything else stays the same. So, you know, I just multiply this by a factor of 3. So that'd be 100. That seems about right. So, makes sense? All right, well, I'll collect your homework, and then I have a new homework, which hopefully won't cause the same troubles as, you know, I think that these homeworks, you know, doing the last test, I realized, you know, that the test problems seem a little different than the homework problems. Just got a different flavor. And then the homework problem, I don't know. So I decided to give you problems that I've written.
Second.
Okay? By the way, if you'll pass the homework down to here, I'll walk over and pick them up. Okay, here's some homework that are being passed out, new homework. If you'll just pass it down, you know, hopefully they'll get around, okay? Okay.
Oh, that is just one.
Easier than having to do 6 months work.
Can we have a stapler? Thank you so much. I don't know what to do, but it's almost